All right, so we're not going to, I don't think we're going to have a free response Friday tomorrow. Darn, I know. We'll pick it up in a little bit, but what my plan is, because this next section is fairly short, we're going to look at some more integration techniques. Unfortunately, okay, these very, very, very rarely ever show up on the AP test. So you might not think that there's any reason to go over them, but just in case, we'll go over them because it is useful to know another integration technique. So we're going to spend today and tomorrow working through this section and on some of the homework problems. And next week, the entire week, can you guys turn to page 81 for me? Do you see page 81? Okay, we're going to be working on that all next week. Okay, so if you read the directions on page 81, it says something like you're going to use any integration technique that you deem is appropriate. Okay, what's difficult about the AP test is they don't tell you which technique to use. So we need to get really good with identifying which one is the best. And sometimes you might have to use more than one technique on an integral. Maybe you start off with by parts and then you have to use substitution in that process. So we're going to do a lot of practice next week with these integrals. So before that happens next week, we just have these trig integrals to go over today. Okay, just as a heads up. Okay, so again, these are very, very rare because if you look at all of those trig identities on there, I don't know who on earth would expect any student to know or remember all of those. So that's why these are normally rare that they show up. I'm not going to expect you to know them. Okay, I'll give them to you if needed. When you're working on your integration practice next week, I'm going to let you use your notes. Okay, just so you can get familiar with the different techniques. But these are a bunch of different trig identities that maybe you saw in pre-calc, maybe we used a little bit last year. We're going to go through and label some of them, but the moral of the story is we're going to have to utilize some of these trig identities to help us solve trig integrals. We're going to use the identities to rewrite some of the integrals to make them easier to work with. Okay, so the first three at the top are what are referred to as your sum or difference identities. And I have no idea if these look familiar to you guys or not. It all depends on who you had for pre-calc, how far you got into the course, all that jazz. Okay? There is something, though, worth noting here about these three. Sometimes when we're given an integral, it might not include this 2 out front, that coefficient. So sometimes we might have to divide the 2 over. We'll just make note of that. Okay, we'll see that today, but just making a note. The next three identities, I'm hoping this one, though, kind of pops out to us. That's kind of the big identity. Sine squared plus cosine squared is 1. Does that sound familiar? I'm hoping. Okay, these are your Pythagorean identities. Because they are actually all based off of the Pythagorean theorem applied to the unit circle. If you're really interested in knowing why, you can just let me know and we can go over it. Okay, but they're called Pythagorean identities. The last ones here are called your double angle identities. if I can spell. Notice how it's sine of 2a and or cosine of 2a and sine of 2a. You're doubling some angle measurement or radian value. So we can represent those double angles as these identities on the other side. Again, just as another note, sometimes we might see sine squared of a within an integral. So if you were to solve this sine squared a portion for itself, you'd have to subtract 1 to the other side. Okay, this cosine of 2a we're going to assume is on the other side, and then divide by 1. So if we did that, the cosine squared of a would be cosine of the double angle, adding the 1 over, and then dividing the 2. Okay, just making note that these are probably going to show up as well. In the other one, if we were to solve for sine squared of a, we would have to subtract the 1 and then divide a negative 2. Again, I don't expect you to remember any of these. I'll give them to you if necessary. I wrote them on the board here so I can reference them as we go through some of the problems, but you can just flip your paper if needed. Okay? So with all of these identities, we're going to utilize them to help us solve more complicated trig integrals. So if you look at the first one, if this was just the integral of sine x, we could do that one really easily because we know that would just be negative cosine. But unfortunately, it's sine squared. So what we're going to try to do is rewrite that integral using one of the identities from above. So it might be a little guessing game because if you take a look at it, we have a sine squared showing up here. We have a sine squared here that we rewrote. So you might not know which one to use eventually, but if one doesn't work or you don't feel comfortable using one of them, just try the other one. So we'll see what happens. You just might have to have an eraser ready just in case it doesn't work out the way we want it to. So can we choose one of those sine squareds? If it doesn't work out, we'll just go ahead and try the other one. So it's, in this case, kind of a 50-50 shot. Can we pick one? We don't have a preference. Let's choose something. Make a decision. It's the hardest thing in life, making a decision. You want to do this one? Okay. So if this, why not? Exactly. If it doesn't work out, we'll try something else. Okay. So if this is sine squared, we're going to have to solve for sine squared like we did in this other case. So we'd have to subtract the cosine squared over. So this integral, instead of writing sine squared, if we subtract the cosine squared over, we would have 1 minus cosine squared. All right, so let's see if we can work backwards from these two terms. If you work backwards from 1 with respect to x, that would just be x. And what if you wanted to work backwards from cosine squared? Isn't that kind of the same issue we had here with sine squared? We have to rewrite it. Okay, so if we got to rewrite cosine squared, again, our options are this guy or this one. Why? Because there's no true function squared. There's no squared in there. Okay, maybe that's something for us to do. Because remember, we said if this was just sine of x, we could do that, right? It was the power of 2 that was creating the issue. So instead of subtracting or going backwards from cosine squared, let's go backwards from an identity that represents cosine squared. So if this is, maybe we'll move the 2 as a coefficient. If both of these are being divided by 2, we can rewrite that division of 2 as 1/2 cosine of 2x, and then plus a 1/2 with a dx on the end. All right, so without that power of 2 in there, we should probably be able to work backwards from this one. If we work backwards from 1/2 cosine of 2x, one-half sine of 2x, and then we would actually have times another 1/2 on the end to cancel out that 2 on the inside. It's kind of a chain rule going on there, or U substitution. And then if you work backwards from 1/2, that would be a 1/2 x. Okay, so that's if we work backwards from both individual terms. If we distribute in that negative, we'll have minus, let's see, 1/4 sine of 2x minus 1/2 x. And then combining some like terms with those x's, we'll have 1/2 x minus 1/4 sine of 2x. So there's our antiderivative using some of those trig identities to help us rewrite the integral. We do know the bounds. We're going from 0 to pi. So we got to plug in top minus bottom. Let's see, if we plug in pi, that'd be 1/2 pi. And then if we plug in pi into our trig function, we would have sine of 2 pi, which is 0. Okay, so minus 0. And then subtract what we get when we plug in 0. Well, 0 for that x is going to be 0. And then plug in 0 there. Sine of 0 is still 0. So looks like we're just left with 1/2 pi. All right, if you wanted to double check on your calculator, you could. You could type that in, get a decimal value, and just make sure it matches the 1/2 pi decimal value as well. Okay, so in this section, we're going to practice rewriting trig integrals by choosing the appropriate identity. And that's kind of the hardest part, is choosing which one to use. If one of them doesn't work, we're just going to try maybe a different one. Okay, let's go ahead and check out the one at the bottom. So I know the identities aren't really on the board anymore because I moved the page, but they're over here if we need a reference. So if you take a look at number 2, does that setup look like anything we kind of have going on with our identity possibilities? The first one. Okay, so notice how we kind of have this setup going on. We have a sine of a value times a cosine of a value. Do you notice how in the integral, though, we don't have that 2 out front? So that means the 2 was kind of divided over to the other side. Let's see what this one would look like if we were to rewrite it. Okay, so can we identify what is kind of the a and b value that's being used in the identity based off the way the integral looks like, or what it looks like? What do you think, Caitlin? There we go. Okay. So if we were to rewrite this integral using the trig identity, we are dividing the 2 over, which is the same as multiplying by 1/2. So we would need 1/2 of sine, and then inside the sine function we need a plus b. but we identified A as 3x and B as 2x, so if you add 3x and 2x, you get 5x. If we continue through the identity, we have to add another portion. Now that was also being divided by 2, because we're dividing the 2 from the left-hand side, so we'd have that 1/2 out front. And in the second half, we need sine of A minus B, so that would be 3x minus 2x, which is just 1x. So instead of working backwards from this original trig integral, we're going to use an identity and try to work backwards from those individual ones. Maybe they're a little bit easier to work with. Okay, so take a look at your first term there. If you work backwards from 1/2 sine of 5x, let's see, we can keep the 1/2 as a coefficient. The antiderivative of sine is negative cosine. We have to keep the inside, but notice how it's a 5x and not just a regular x. So that chain rule idea has to be kind of canceled out. We'd have to multiply by a 1/5, which is the derivative of that inside. So that's backwards from the first term. If we work backwards from the other term, we can keep the 1/2. The antiderivative of sine is a negative cosine. And same idea, you would have to multiply by 1/1 though. Okay, the derivative of the inside, but that's not going to change anything. We don't know the bounds, so plus c is a good way to go. And maybe we can clean it up. At least the first term we have a 1/2 times a 1/5, so that'll give us a 1/10. We doing okay so far? Okay, it's about rewriting, or at least trying to identify which trig identity to use. Alrighty, let's try the next one. So, does that one look like any of the ones that we discussed? Can we maybe rewrite some portions? Yeah. Okay, so maybe instead of using an identity right off the bat, maybe we can just rewrite it algebraically. So if we have sine cubed, that technically means we have 3 sines being multiplied together. So maybe I'll just write 1 sine first times 2 other sines. Does that make sense? And this would be a cosine squared as well. Okay, so that's one way to rewrite it. We just didn't use an identity. Did you want to keep going from there, or? Yeah? Okay, what do you want to try next?
I was going to say we can change sine squared x cosine squared x into the identity.
Okay, so which one do you want to try? Or which one do you want to read? This one?
Yeah,
the top one at the top of the list.
Substitute sine x and then multiply by the identity, because then your sine of a minus b is going to cancel, so you get sine of 0, which is just 0. So you have sine of x multiplied by sine of 2x, and then you can do the third one.
When you say top one, you mean this one?
Yeah.
You mean the third one? Because this would be sine of x, sine of x, right?
Yeah, actually, I forgot to do that squared.
Okay. If it's squared, though, we can use this one or that one that's rewritten.
Yeah.
Do we have a preference? Do you want to use the Pythagorean one or the double angle one if you want to rewrite this one? Double angle? Okay, so sine squared, double angle we said, let me get it, that was cosine of 2x minus 1 all over negative 2. Is that right? All right. So maybe we can start to simplify it a little bit. Let's see, if we distribute in a sign, and maybe we'll bring out this negative 1/2 on the bottom as, or negative 2 on the bottom as a negative 1/2. So we'd have a negative 1/2 sine x times cosine of 2x. And then, if we distributed that in here, we'll have a negative 1 divided by a negative 2, so it'd be a positive 1/2 sine of x. But that's still all multiplied by the cosine squared x on the end. So technically we'd have to distribute in the cosine squared. Do you think it's getting more complicated for us? It looks like it? Okay, so maybe we'll abandon ship. Okay. I told you guys, get your erasers ready. Okay. Do you want one? I have an eraser. Do you want?
Do you have the pencil?
Yeah.
Oh my gosh. I saw that erasers like 3 weeks ago and it saved my life.
Yeah.
Oh,
Yeah.
guys, there's different colors. I'll grab one of these.
All right, so we're abandoning ship, and instead of using the double angle identity to rewrite sine squared, maybe we'll try the other one. So that would be the Pythagorean. To get sine squared by itself, you'd have to subtract over the cosine squared. So 1 minus cosine squared of x. Let's see where we can go from here. Let's try I'm going to give you guys a little hint. What if we tried another type of integration here? What if we tried u sub? Okay. We got to choose something that kind of looks like it's on the inside, but I don't want you guys to get too caught up in that concept, because I know when I say inside, you guys think parentheses, right? 1 minus cosine squared is on the inside of those, okay? But couldn't you technically also write cosine squared as cosine of x inside parentheses? Okay, so don't get caught up that the inside's always parenthesis values. Okay, it could be powered values as well. What if we let u be cosine of x? Because that's kind of on the inside of this squared idea. Then the derivative of cosine is negative sine, right? Do you see how that derivative is also showing up within the integral? So that means when we go through u substitution, won't those eventually cancel each other out? Okay, so that seems to be something we could try. Let's go ahead and see what happens. So we're going to have a sine of x, and then we have 1 minus cosine squared, but we're letting cosine be u. So we can write that as u squared. And again, we have another cosine squared, so we can write that as u squared. Instead of dx, if you solve your derivative for dx, we'd have du over negative sine. And do you guys notice how those signs are going to cancel out? Aren't the x's going to go away? Okay, so it looks like we have a 1 minus u squared times a u squared times the negative that's left over from that sign that canceled out. So if we distribute all of those in, looks like we have a negative u squared plus a u to the fourth. Do you think we can easily work backwards from that integral? Backwards from negative u to the squared? Negative 1/3 u cubed. All right, and backwards from u to the fourth? That'd be a 1/5 u to the fifth plus c. So we simply have to substitute in what we let u be, which was cosine at the top. So we have 1/3 cosine cubed plus a 1/5 cosine to the fifth plus c. I will give it to you. These are going to get kind of difficult, okay? But to be honest, the ones we do together in here are going to be more difficult than the homework and the mega integration ones, okay? If we can do the hard ones together, I think you guys can try some of the simpler ones, okay? Let's go ahead and take a look at 4. Anything you guys feel like doing when you look at that? Besides crying? No? Expanding. Let's get rid of the squared, okay? So if you were to write it twice and go through distribution or FOIL, we'd have sine squared plus 2 sine x cosine x plus cosine squared. Okay? Now, can we take a look at what we have in there and perhaps identify any identity that's showing up? Or identities? Yeah?
Sine squared plus cosine squared.
Okay, so they're not necessarily in order, but notice how you do have a sine squared plus another cosine squared. So based off of that identity, what can we simplify those values to? Yeah, would be 1, okay? So the sine squared plus cosine squared is changing to 1, and we still have the middle term 2 sine x cosine x. Okay, can we work backwards from 1 with respect to x? That's just x, right? Okay, can we work backwards from 2 sine x cosine x? We can use an identity, okay? So how can we rewrite 2 sine x cosine x using one of the identities? What would it look like? I think those are the A and the B ones, right? So we have x as A, but also x as B. They happen to be the same thing. What would it look like? Let's see. 2 sine of A cosine of B equals In this case, we don't have to divide the 2 over because you see how it's showing up in the integral. The division's not necessary. So the identity would be sine of a plus b, or in other words, sine of x plus x, which is 2x, plus sine of a minus b, but sine of x minus x is just 0. Do we know what sine of 0 is? Cosine of 0 is 1. Okay? So this is actually going away. Sine of 0 is 0. All right, can we work backwards from that integral? Now that it's just a simple sine, the antiderivative of sine is we got negative 1/2, good. Cosine of 2x plus c, perfect. Works for me. That wasn't as bad as the last one we did. Alrighty, let's check out 5. Anything you guys feel like doing? Let's see, I see a sine, yeah.
Using the double angle.
Okay, so cosine squared, it's either going to be the Pythagorean or the double angle that we can solve for. So you got to choose one. If it doesn't work out, go ahead and try the other one. So Eric wants to use the double angle. So that would be 3 times, because we're going to rewrite the cosine squared part. So we need cosine, and according to the double angle, it's 2 times a, but notice how your a value is 5x, right? That's what your angle is representing. So if we take 2 times that, it would be 10x. We then have to add 1 and divide by 2. Dx on the end. So if we clean up that integral, distributing in the 3, maybe we can pull the 2 out though as a fraction. So this would be 3/2 cosine of 10x plus a 3/2 on the end. All right, let's see if we can work backwards. So we can keep the 3/2 as a coefficient. Antiderivative of cosine is sine. Keep the inside, but we gotta counteract that chain rule. And normally we divide by the derivative of, normally we multiply by the derivative of the inside. So to counteract that, we'd have to divide by the derivative of the inside, or in other words, multiply by the reciprocal, which would be 1/10. And then antiderivative of the second term, we would just have 3/2 x. Don't know the bounds, so plus c. So simplifying, looks like we'd have 3/20 sine of 10x plus 3/2 x plus c. I don't think that one was too bad either. I think that's more representative of the ones that we're going to take a look at in the homework and on the mega integration. Okay? I think we'll stop there. We'll save the last page for tomorrow just as some refreshers, okay? If you want to start to try some of the homework ones, you can. I don't think I gave you a lot. Okay, yeah, just 11 problems. But it's all about rewriting and not quitting.